Hello and welcome to today's group meeting. In today's seminar, we have Tjoa, who's going to talk about entanglement harvesting versus communication. Very interesting. So Erickson, the floor is yours.
Thank you very much. Also, I think this time around you got the pronunciation of my surname correct, so that's excellent. So anyway, today I'm going to talk about a project that has been going on for a while, and I will explain to you to some extent later near the end why this thing took longer than it is expected for a good reason. But it will be something of quite an interesting topic, namely entanglement harvesting versus communication. And I will make clear why the title is chosen as such. So first, to guide the progress, because it is a little bit of like a messy business, I will start with an introduction of why we are doing this. We will also briefly review entanglement harvesting protocol, which in this group will be sufficiently familiar with. And then we will present some results in 3+1 and 2+1 dimensions. We will mention the connection with strong Huygens principle, and we will also bring up what I like to call in this project a pesky thorn in the throat. Right? It's basically what happens when you demand that you need compact switching, and then we will go on and discuss a little bit about higher dimensions and massive scalar fields before we conclude with the thing. A small warning about this presentation is that this will be mostly words and pictures, and if there's any formula, they are mostly straightforward and not highly non-trivial. But if you need some formulas near the end, I can present some of it. But essentially, I think this is the better way of presenting what's happening in general. So first, these are not exhaustive lists of work that has been done for many years, but entanglement harvesting protocol has been investigated in many situations, and it is essentially the protocol where you have two non-relativistic quantum probes, such as under-the-way detectors, which extract entanglement from the vacuum of the field they interact with, and they couple locally to the field. And what is notable about this protocol is that it relies on the fact that vacuum state of quantum fields contain a lot of classical and quantum correlations. And this is really a deep result from algebraic quantum field theory. And these two detectors can extract this entanglement even when they are space-like separated. And this is a result that has been around for at least 6 years now. And the protocol has been shown in the past few years to be sensitive to various things of fundamental interest. For example, it can be a good probe for background geometry, boundary conditions, detector state of motion, and many other things that are of interest to many people. It is even useful, for example, for range finding and thermometry. Now, the question that is somewhat not very obvious when people start doing research along this line of attack is that whether vacuum entanglement should be really thought of as something that is independent of the causal connection between the regions. Because, for example, from a more algebraic or mode decomposition, the Bogoliubov transformation kind of calculations, what you get is that so long as the regions are already correlated if they are disjoint, even if they can be causally connected. So even if they are not inside each other's causal complement. So, but what is not obvious is whether this vacuum entanglement is actually kind of uniform, like whether two regions of space-time, they are like space-like or time-like separated. If they are the same regions, if they are, for example, two diamond wedges of the same size, are they going to have the same amount of entanglement? And this is really a difficult question in general. And under-the-way detector type of calculations tends to make this into another variant of the problem that is actually easy to understand. And the way to do this is essentially as natural as it can get. Basically, you just take two detectors on their own respective trajectories. You can then put them in the sense of relativity, whether they are causally connected just by putting them in an appropriate trajectories in space-time. Now, but once you allow causal connection between two detectors in spacetime, if there is quantum field around them and they interact locally with the quantum field, then now you are essentially opening a communication channel between the two detectors. The reason is because the field is essentially providing you with a wave propagation, and that wave propagation can be used to actually propagate information. And therefore, it is important to ask whether how much of this entanglement, if the detectors are actually not space-like separated, really come from entanglement swapping from the vacuum. Because in general, interactions that you can think of often are entangling in nature. Like it has to be somewhat a subset of certain classes of interactions. They are actually entanglement breaking and not generate entanglement. And another way to think about this is to ask, what is the role of field-mediated communication in entanglement? Does it simply add on top of the vacuum entanglement you get already? So in a way, should we really be thinking about vacuum entanglement harvesting for timelike separated for causally connected detectors to be vacuum entanglement harvesting plus something extra? Or is there something more interesting going on here? And this is something that is basically not obvious at all if you just stare at the protocol, because it is really a deep property of the wave propagation in generic spacetimes. And this is essentially the punchline of these slides. I hope this doesn't come as too strong, but essentially we will show that when two detectors are causally connected, not all of the entanglement that you get at the end really comes from the QFT vacuum. And in many relevant, interesting situations, essentially you can regard all of them essentially comes from communication. And this result is really robust, regardless of whether strong Huygens principle applies. By this, I mean that even if strong Huygens principle is violated in the sense that there is wave propagation in the interior of the light cone, you will still have something analogous. And this is the reason why we are going to look at 2+1 dimensions later. And for these results, we are going to consider several situations with a bunch of pictures and plots and show how the communication plays a role in all this entanglement story. So first, let me start with a somewhat boring part for this group, but for people watching the video, it might be a somewhat good refresher. The protocol essentially starts with with a sum of two locally interacting Hamiltonians between the detector, each detector interacting locally to the field, but there is no direct interaction between the detector and the other detector. And Hj, for all practical purposes, we take it to be the standard UDW Hamiltonian. You can easily change this to, for example, harmonic oscillator type of detectors. We will be considering qubits kind of Unruh-Lewis detector with two levels. And the standard vacuum entanglement harvesting protocol, as the name suggests, it will start with three initially uncorrelated ground states of each Hilbert space. So you start with a ground state of detector A, ground states of detector B, and then the ground state of the scalar field, in which case is the vacuum state of the free field. And then we will consider, and then the final reduced joint density matrix after you do time evolution using this Hamiltonian will boil down to simply this after you do the Dyson series expansion. In other words, after you do perturbation theory to leading order. So basically you do time evolution and then you partial trace the field and then you get this reduced density matrix of the two qubits. And then for completeness, this is one of the rare cases where I will show you the formula. Essentially, you have a bunch of LAA, LBB, which is essentially the transition probability of the detector from the ground state to the excited states. And LBA and LAB together with M are actually the non-local kind of matrix elements. And by non-local, I mean that it simply depends on trajectories at it depends on the trajectories of both detectors. It is not really at one single trajectory of a single detector. Now, once you have these matrix elements, which depends on energy gap of the detector and how long and how strongly you turn the detectors on. You can compute the entanglement at the end of the interaction by, for example, an entanglement measures like negativity, which is basically the trace norm of the partial transpose of the reduced density matrix. And in this case, because we are going to restrict ourselves to the simplest case of a Minkowski spacetime, and also restrict the case where the detectors are at rest relative to the Minkowski frame, the laboratory frame, the one with the standard Minkowski coordinates, this negativity to leading order is going to simplify into something very simple. It will just be the absolute value of the M term, which is the top right and bottom left corner, minus transition probability of detector A or detector B. It doesn't matter because they are the same due to translational invariance of the spacetime. And that's essentially the summary of the protocol. If the negativity is greater than 0, which for two qubits is a faithful, necessary, and sufficient conditions for entanglement, then the detectors are entangled, otherwise it is not. And it is also entanglement monotone, which means that you know that it is more entangled when you go when the negativity is higher. Now, in order for us to talk about communication, what we need first is to actually conveniently split the Huygens function that appears in the matrix elements. The Huygens function is essentially the 2-point function, the vacuum expectation value of the field 2-point function. And we'll split them into the anti-commutator pieces versus the commutator pieces. We know the commutator is the one that controls communication because this is the part that exactly vanishes when they are space-like separated. And this is also state independent. So to some extent, this is somewhat the classical object. While on the other hand, this one is a state dependent part. And this is the one that really controls the vacuum entanglement part, because if you do space-like entanglement harvesting, then this is really the only contribution that comes along with this. And because you can split the Huygens function like this, then you can conveniently split by linearity the non-local term M as M plus and M minus, where M plus is the anti-commutator part, which we will call the harvesting part of M, and the commutator part will call it the communication part of M. Okay? For all practical purposes, we'll be talking just about scalar fields in this talk, but I would expect that further work will show that this is actually generic features of standard quantum fields. Now, this splitting, which is based on the commutator anti-commutator split, will also motivate us to conveniently check if we can if the negativity comes from communication or harvesting. So we will simply apply negativity into just the M plus or M minus and ask ourselves what is the outcome. The intuition behind this is that for space-like separator detector, clearly our argument says that the M0 should be basically 0, and therefore all negativity must come from the harvested negativity. Or alternatively, you say that basically the communication assisted negativity is basically 0. And then once you have this, a convenient way of representing the results would be to define an estimator, which for lack of better words right now, I would call it communication-based entanglement estimator, which is simply the ratio of the communication-based negativity divided by the total negativity if it is greater than 0, or if there is no entanglement already, let's just declare it 0. Now, this is basically just for convenience, because by normalizing it like this, then your plot is just going to be a range, your plot will basically range from 0 to 1. And the interpretation of this is that if this answer is approximately 1, or essentially 1, then you're essentially declaring that all entanglement comes from communication. Okay? If it is in between, then typically you would expect that this is a mixture of both of them. But if this is very close to 0, then you either originally have no harvesting at all, or all of them comes from harvesting. And the way to distinguish these two is to just check whether n is actually greater than the script n is the negativity is actually greater than 0. If it is greater than 0, then it is the second case. If it is already starting from 0, then it is the first one. with that, we can now show the results. So first, for 3 plus 1 dimension, what you can see is that on the left, I plot the estimator, entanglement estimator, and on the left, I decompose the plots into 3 different kinds. One of them is the negativity, one of them is the harvested negativity, and the other one is the communication-based negativity. And what you can see is that on the left, the entanglement estimator actually peaks at the light cone, and this peak is maximal in the sense that basically near exactly where the light cone is. And here the light cone, I measure the light cone peak as basically from the peaks of the switching functions of the 2 detectors. And what you see is that essentially at the light cone, practically all of them come from entanglement. I mean, technically it's exactly, but you see that the communication really dominates much of the entanglement that you get at the end of that thing. And this is actually interesting because if you look at it on the second plot in figure B, what you see is that the communication-based one starts to dominate when. So the blue region I plot here actually is kind of like a way to visualize when the behavior of the n plus and n minus starts to change. And you will see that once the blue region, and once you are in the blue region, the n plus starts to drop actually very quickly. Okay, while the communication part starts to climb very quickly, and then that's essentially the story. The story is that the harvesting part miraculously kind of like what's the word? The harvested and negativity basically just disappears. And this is the reason why. So this answers the original question: does the communication simply adds on top of the entanglement? And the answer is no, because in this case, for massless scalar field in 3 plus 1, what happens is that the moment the detectors can get entangled via communication, it will kind of forego the ability to actually get entangled by swapping. And this is kind of like somewhat counterintuitive because the vacuum is kind of like always ever present, so you would have thought that anything else should simply add on top of it. Now, the central region, the white region in the center here, is basically the spacelike, effectively spacelike region. So these are way outside the strong support of the Gaussian function. So this entanglement can be regarded as basically spacelike entanglement harvesting. So in this case, the spacelike entanglement harvesting is not 0, and you can check that the communication based one is essentially 0. The pink color here I have mentioned in the caption is essentially just for me to kind of catch this roughly 3.5 sigma width. This is basically 3.5 units of the switching time on the left and the right of the light cone to mark, roughly speaking, where you think the strong support of the detector should be. And this is how I mark the spacelike separation. Okay.
Sorry, Erickson, this is all for a massless field, right?
Yes.
Would you expect this to change for a massive one?
In the outline, I say that I will present a massive scalar one. So.
Oh, you will also talk about it. Yeah, sorry for that.
Yeah. Okay. Next, let's go to 2 plus 1. Because in 3 plus 1, we know that there is this thing called strong Huygens principle, which I will explain in 2 slides. Essentially, the strong Huygens principle says that the communication part of the field should be strictly on the light cone, which is the reason why these plots on both ends are dominated in the neighborhood of the light cone. But in 2 plus 1, slightly different story appears because there is no strong Huygens principle, which means that even though the field is massless, the wave propagation, the Green's function, has actually support in the interior. And so what happens is that you don't expect things to disappear out in the interior of the light cone, and true enough, this is indeed what happens. So if you look at the plot, right, what happens again is that once you start to approach the light cone, the communication component starts to climb, and then it will eventually become essentially all the entanglement that you get as you approach the interior of the light cone. And then the only subtlety with this estimator is that this sudden precipitous drop is just because you know, as you increase the space-time interval between two detectors, the non-local term always decays kind of somewhat polynomially, but the transition probability is always a fixed non-zero constant. So eventually, once you are deep enough into the light cone, you are essentially going to have zero harvesting. But essentially, the crucial point of this plot is that your communication component essentially approaches unity. So you essentially, and this is not because the communication simply dominates the harvested part, but rather also because the harvested part kills itself. So you can see that in the space-like region, the harvested part is the main contributor to is the only contributor to harvesting. But the moment you enter the blue region, that means as you approach the light cone, just slightly before the light cone, it starts to decrease very quickly on its own to zero, and while the communication part will start climbing up, and then it will dominate. Now, and then somewhat a little bit confusing part of this is that the communication part here disappears not because there is no communication in the interior. It's because there is the M term, the non-local term in the density matrix, always continues to decrease, and eventually it will decrease below the local noise of the detector. But the point is that the communication always dominates in the region where the harvesting part actually self-decreasing. So this is kind of like, and this is a little bit different because now you see near the light cone, they kind of conspire together to actually contribute both to the entanglement. So in this case, around the light cone, they are sharing the vacuum entanglement harvesting with the communication-based one. But it's true that the moment you get past into the interior, then the communication takes away everything. So essentially, for example, here in the blue region in the interior, you essentially see that the blue curve, which is the total negativity, is essentially all communication. Now, I've been throwing this phrase about strong Huygens principle, and let me iterate that this is basically a statement about how massless fields, in this case scalar fields, in n+1 dimensional Minkowski spacetime has a Green's function that is supported only on the light cone when n is odd. There are generalizations of this to curves, to some specific classes of curved spacetimes, like those that are conformally flat to this one, but we'll let that slide. But the crucial point is that it is under strong Huygens principle, if your spacetime has strong Huygens property, then the communication part has to be dominated only when they are null separated. So in our previous slide, what you have seen is that the commutator piece vanishes in the timelike region, but it is dominated in the neighborhood of the light cone. But in the 2+1 dimension, you do see the commutator being significant near the light cone, but it also leaks into the interior, and that's the reason why that's why if you plot the commutator itself, right, it is actually non-zero in the interior. So to summarize, before we move on, these two specific cases already show us that in the interesting case that we know very well, it is not the case that communication simply adds on top of the vacuum entanglement harvesting. Okay, in fact, the story is that communication dominates and harvesting will actually vanish near the light cone. So basically, when one goes up, the other one goes down. So it is not just add. The same story essentially persists for 2+1 dimension, except the way they contribute at the light cone and in the interior. But the story is still the same, that the harvesting, the detectors essentially, the moment it sees that it can use communication channel mediated by the field, it will kind of just forget about entanglement swapping with a vacuum and just try to get entanglement via the wave propagation itself. Now, this is the pesky thorn, okay? An intelligent demon might just ask me one day and check if maybe everything you're saying is just because you're using Gaussians, right? I mean, like, if it is all Gaussians, and Gaussians are technically speaking, if you're being really strict, they are always causally connected, then are you not cheating, right? Well, actually, to dispel this argument is actually not that difficult, in my opinion, but there is a good reason why such a demon is hard to kind of like dismiss, right? So one is that most compactly supported functions lacks analytically tractable expressions for raw AB, which means that contrary to what you might expect, it might actually be quite hard to even get reasonable answers in the regime of parameter space that you are interested in. For example, if you want omega, the energy gap to be really big, then oftentimes lack of analytic expressions really make things really difficult. But the more important factor is that compact switching is comparatively noisy in the sense that if you compare it with a Gaussian switching, right, even the excitation probability is way more suppressed for smooth switching than the compactly switch one. And this is true even, for example, if you consider stuff like this. So for example, if you take this cosine switching that is supported only in the interval minus a comma a and 0 elsewhere, this switching is C infinity everywhere except at a corner, which is continuous, and you can actually check that for all the standard parameter space that people use, you cannot even harvest do entanglement harvesting at space-like separation, and in fact you cannot even harvest entanglement at null or time-like separated. So you essentially just get 0 for everything, which means that this thing is practically useless for doing exactly what we have been doing for the past few slides.
Erickson, well, I agree with the spirit of what you said. I'm not sure if the claim is true as you have it, right? You haven't really checked what happens with omega, right? Like capital omega. Can you tell really that it's impossible to harvest with this?
Well, I check it. I check it up to omega equals to 10. It doesn't work.
Right, but it's all numerical checks. That's what you mean, right? Like it's not that you have a theorem or you have a result saying that this will not be able to harvest, correct?
Well, I mean, essentially, whatever results you want to call it here is as good as the plots you have in the POSAS paper. You didn't check everything either, right?
Yeah, no, I agree. But the claim that you have here is, I mean, again.
Yeah, it might come as.
This is not an attack and definitely not a comparison. What I mean is that the claim is not checked completely. It's just basically that it's extremely difficult, very likely, extremely difficult to harvest.
Essentially the way to argue about this, and I think in the numerics, essentially this is the evidence I'm employing, is the fact that the non-local M term, the modulus, right, is actually kind of like the pattern it always appears is that it will, as you increase the energy gap, it will eventually climb up and then it will eventually go down at some point, right? And that pattern of going down is the one that is continuing to happen as you increase omega, and that's the only indirect evidence I have. You're right that if, let's say, miraculously somehow I increase omega, then the M increases and then it decreases, and then miraculously when omega is like 1000 it starts increasing again, then of course yes, that's a different story. So you're right, I don't have a theorem for this, but I think the standard evidence would be this. So maybe I came as too strong for this, but I think this is more than enough to argue that the compact switching for 3+1 doesn't actually going to work, at least not using this one. I mean, maybe cosine to the power of 4 or to the power of 100 might work, but I don't know. Is that okay, Eduardo?
Yeah. The one thing that is interesting, perhaps, to study more formally at some point by someone, right? It's giving bounds to the integrals, because of course maybe we won't be able to solve the integral. Maybe we can bound them and then prove that the noise is larger than that, depending on the switching.
Yeah, it might be possible to find bounds. It's just that I think for this sort of integrals, they are complex valued and with heavy sides, a bunch of it, right? I think it's going to be very hard to get a tight bound. That's the only issue. But we can talk about that a little bit later at the end. I think this is itself an interesting thing. And unfortunately, this is a bunch of, for compact switching, is a thorn that is kind of riddled with a bunch of bad news. Now, the one indirect argument I would bring it up first is that that in an argument that we can provide to such a daemon for why this phenomenon has nothing to do with switching in general is the fact that in general, as you become more causally connected, that means as you approach the light cone and start to enter the interior, the general pattern is that the M plus modulus always decreases quickly while M minus always increases. And even with the strong Huygens principle, right, with or without, as you can see in the 3+1 and 2+1 dimensional representatives, the M plus and M minus always decreases faster in the light as the light cone interior is approached. And of course, my result has been using Gaussian switching because that's where convenient results appear. But if you do this for 3+1 dimension, this pattern I just mentioned in the first 2 points actually also holds. In fact, 1+1 is sort of the extreme case where the moment you enter the light cone, the commutator approaches a constant, which means that the decay in M minus is completely controlled by your switching function. There's nothing about the field anymore. While the anti-commutator still has an extra kind of like a polynomial decay coming from the Hadamard part, from the anti-commutator piece itself. So that means if you are using compact switching, which typically has a polynomial tails in a Fourier transform, right? Then in 1+1, the commutator part adds no extra polynomial power, but the anti-commutator part adds extra powers to the polynomial. So that in general, you expect the anti-commutator pieces actually decreases faster than the commutator. So this general feature has actually nothing to do with the compact switching. I will show you one plot later at the end if you are interested, but I relegate it to the appendix because I think it is not relevant. But this is essentially the story, the story in the generic dimension. I've also checked this for Gaussians in higher dimensions. So this is going to be common. But let us be more explicit. So there are two other cases of interest, at least at this point, that we need to kind of like get rid of. One is that what happens when you are in higher dimensions? Because, for example, we know that the strong Huygens principle applies only in alternate dimensions, alternate like every odd and spatial every even dimensional spacetimes, while the massive and then we also have another case where you have massive scalar fields, where massive scalar fields, what you see is that because of the mass, the commutator itself naturally leaks into the light cone in all spacetime dimensions. So for massive scalar fields, there is no equivalence, or there's no strong Huygens principle equivalent kind of thing to confine everything on the light cone. So in higher dimension, what you see is essentially the pattern occurs the same as the 3+1 and 2+1, except that now, for example, in 4+1, you expect that similar things happen to 2+1, which is right, because you see that there is a leaking into the light cone. And remember, there is a sharing of entanglement between the communication and the Hadamard pieces here. But now you have an extra peak in the n plus and n minus, and that means there's extra peak in the scry I, the estimator of the entanglement. But it is still true that as you go deep into the light cone, then you essentially take almost everything in as communication. There is an extra peak here that is also dominated by communication. We'll see what happens to this later. Now, in 5+1 dimension, which is essentially where a strong Huygens principle also applies like 3+1, again, you have multiple peaks. But now, interestingly, the peak arranged, because it is around the light cone, right? The peak arranges itself in such a way that essentially now, exactly, basically right at the light cone, you are not, the communication no longer dominates. It dominates slightly on the left and right because the way the peak is distributed. So to some extent, we can still say that the communication is the dominant part as you approach a light cone, but it has this peculiar dip at the center. So in this case, if you look at it, actually the n plus, the harvesting part, actually dominates when you exactly arrange the switching peak to be at the light cone. So if you look at this naively, right, you might think that 5 plus 1 result contradicts the results in 3 plus 1. So what is happening here? And the short answer, well, I'm not sure if it is short, but this is another place where I will show the formula, is that this has to do with the fact that the commutator in arbitrary dimension goes with the Dirac delta functions and its distributional derivatives. And it is supported on the light cone. So what you see here is that in higher dimensions, your commutator is a sum of Dirac delta functions and its distributional derivatives, and the dominant part is the one that goes with the least power of x, is actually the highest distributional derivatives. Now, because they are distributional derivatives of the delta functions, they are also still supported at the light cone when the strong Huygens principle applies. But the problem that is different is that the nascent delta, the nascent family of the distributional derivatives of Dirac delta functions actually have a j plus 1 peaks. So the way to think about this is that if you think of Gaussians, a family of Gaussians as a nascent delta functions, as a nascent delta functions, then the distributional derivatives has a nascent delta that comes from derivatives of the Gaussians. And you know that every time you differentiate Gaussian once, you gain extra peak, and then when one peak at the top and one peak at the bottom, and then when you take a modulus sign, which is what happens when you compute m, the peak will flip up, so you gain extra peaks. And what happens is that if you can just check this by brute force or combinatorially, that in general your n plus minus gain extra peaks for every dimension, every even or odd dimension they climb. So for example, in n plus 3 spatial dimensions, there's always one extra peak in your n plus and n minus than the n plus 1 correspondent part. And that's exactly what happens in the 4 plus 1. The 4 plus 1 has one extra peak compared to 2 plus 1. The 5 plus 1 has an extra peak in than the 3 plus 1. And you can check this. I checked this up to the 7 plus 1 dimensions, and it's true. So for massive scalar field, something funny also happens. But the story, this is where the robustness that I mentioned appears. So remember that for massive scalar fields, the commutator naturally leaks into the light cone. But what happens is that you can show that while in the space-like region, the communication does nothing, but the moment you approach and enters the light cone, the harvesting and the communication part will start alternating each other and contributes more or less kind of equally in every part. So you can see that they kind of weave together. When one is minimized, the other one is maximized, and so on. And you will see that the entanglement estimator, the communication based one, is going to alternate back and forth as inside the light cone. And this will continue along. And this is very interesting because normally when people compute negativity, they are going to only see the total one, which is blue, which is just one smooth, nice curve. But when you decompose them out, this is what you get. And so this is where it is kind of like a very interesting thing. Another observation you can make is that now you can ask how these oscillations has to be controlled by the mass, right? Because that's the only extra parameter compared to the massless one. And the answer is yes, because what happens is that, remember, the mass m enters through the exponential of the plane wave mode. So your plane wave mode has e to the power of I omega t, and that omega enters m. So essentially the higher masses adds more oscillations to the interior of the light cone. And you can check this by simply, I checked this, but you can basically try and lower m slowly, and eventually at some point the number of oscillations will decrease so much that it will decrease to the number that you see in the massless case. So for example, if when m is around 1/100, as far as entanglement harvesting is concerned, it has the same number of peaks almost as the ones you get in the 3 plus 1 massless case. And essentially that's the story I would like to tell. It's not really very long, but the takeaway is that from all these observations, what you can see is that entanglement harvesting protocol, in general, if you're being really careful, should be really regarded as the protocol between two space-like detectors. Because what we have seen in this presentation is that just being able to communicate does not add entanglement on top of the vacuum swapping. It takes away the ability of swapping entanglement with the field. And therefore, this is something that one has to be really careful about. And this also highlights the significant role of two-party communications in entangling two detectors. And it is significant in the way that it is really a robust feature of wave propagation. Like you see quantitative differences in massless and massive case in higher dimensions, but for the most part, the commutator essentially takes the spotlight. And that's why one really has to be careful about ascribing entanglement that the detector obtained after interaction to really the vacuum entanglement. And this is important, right? Because a lot of times we say that detectors probe the vacuum entanglement structure of the field, but this is really just this is almost saying that what you end up probing when you can communicate is the probing the communication capabilities using the field. And for example, this is relevant in, for example, the curved spacetime, because we know that the commutator is highly non-trivial. Eduardo has a few papers on this. And I also have a paper on black hole spacetime 1+1 dimensional reduced one. Now, in those cases, you now have to start to be very careful about it because the redshift masks the causal relations in many ways. And even in 1+1 model where you don't have the angular pieces, you also have to be careful because the derivative coupling, for example, right, is to some extent kind of mimicking the Minkowski space part. So what you expect actually is that the same results in Minkowski space actually will leak over to any 1+1 models that tries to avoid the usual IR divergences. Now, this will also mess with indefinite causal order if the temporal ordering, the superposition of temporal ordering, needs to make them explicitly time-like connected. Because what it means is that if indefinite causal ordering based kind of harvesting protocol claims that they harvest more, right? It may be not because there is anything to do with the vacuum entanglement, it's just because they actually improve quantum communication, which is actually a well-known result in indefinite causal order papers, right? And the last bit is that there's also recent work on delocalized detectors, for example, by Nadine and Richard, that shows that if you quantize the center of mass of the detectors, then in general, the spatial support is going to leak in a non-compactly supported way. And when this happens, right, that means in general, on top of the causal connection due to the switching crossing each other's icon, now you also have to fight the spatial smearing part. And we expect that this result will still be true even if you include spatial smearing, because I think while in this work, I didn't consider dynamically generated smearing like the ones you quantize the center of mass. But I think the result generalizes straightforwardly to spatial smearing, and I think not much. You don't lose all of any of the essential results that we get here. And essentially, that's the end. I have some appendices, but that's only if there's anything to deal with. And I think that's the end.
All right, thank you very much, Erickson. We go to questions. I have one comment to make. This is pretty cool. There's one thing that I would like to do as well, because of course so I obviously fully agree with this. So I propose the use of this estimator. But something that devil's advocate, I haven't been told this by anybody, but somebody that can say is like, how can you be sure? Okay, I agree. When you space-like separated, the commutator is 0. All the harvesting is harvesting. All the entanglement is harvesting. I also agree that the commutator part estimates the strengths of the communication terms. How can you be sure that it's not harvesting through the commutator? It's like you're kind of assuming that the things that happen through the commutator are communication, and I fully agree with that. But if you want to really certify it 100%, I have another toy project that could be for an undergrad student or something with working with a grad student, which is about really checking in a toy model where you have a chain of harmonic oscillators, where you can actually check the entanglement in the chain of harmonic oscillators. When you're actually decreasing the amount of entanglement, when you're actually harvesting the amount of entanglement from the system. I do think that what we do is the right thing to do, but that's as an extra check of under what conditions you are generating entanglement through communication versus actually decreasing and transferring the entanglement from the chain. That's a different kind of project. I do fully agree with this, but I think devil's advocate, somebody could always ask, okay, cool, you're giving strong evidence to what you're doing. It's not quite approved yet. But just mentioning that. It's certainly, for me, it's like super strong evidence. Certainly the communication dominates. It's gonna, this is not calling it harvesting is super dangerous. It's sushuden because it's very likely not harvesting.
Yeah, because as you can see from the estimator, it approaches unity. It's not just going something high number. But
yeah. Anyway, that's my comment. Does anybody have any questions? I have more comments, but I'll wait until questions. I have comments about the massive case and so on. Well, there aren't any yet. For the massive case, that oscillation to me, one way of interpreting, and maybe we can discuss it. Can you get the plots? Yeah, one way of interpreting is like in the timelike area, you're doing both kind of at the same time. It's true that when one peaks, the other one doesn't, but if you kind of average over where you place the detector on average, because it's gonna some width, in general, you're probably gonna be doing both, right? I mean, you're gonna get some of those. So it's kind of when it's massive, you're doing both at the same time in your timeline, which kind of makes sense.
Yeah, and it makes sense, right? Because if you see, right, the way they oscillate, right, it's kind of like in a destructive interference kind of way, right? So whenever one goes high, the other one goes low, and they just interchange among themselves. And actually, if you take the what's that called? The imaginary part of the Huygens function in the massive case, you can actually see that this oscillation matches exactly the oscillatory part of the Huygens function in the imaginary part. So it just comes out of the fact that the Huygens function for massive scalar field has a commutator that is oscillating.
Right, but you see, if the mass were large enough as compared to the other scales, a detector would not see the oscillations. We just average.
Exactly. The whole thing would be oscillating so quickly that you will just see a whole thing just bunch up. So for example, if mass is so heavy, then you don't have this space where they manage to share. Like.
That's right. So then you can't say effectively if it's massive really. You're doing both at the same time, you can really separate kind of thing.
Yeah, you really cannot cleanly separate. Well, in this way, you can still kind of like move the detector kind of slightly there while it's 80%, you know, like, yeah, that's right.
But there you're scaling the mass by the time duration, essentially, right? So the mass is
I'm just choosing one unit that is convenient.
Yeah, sure. But it's like, what I mean is essentially, I don't know, I'd like to know, like in physical terms, like using, I don't know, it's hard to probe like massive fields, but the only physical example that actually comes to mind is the neutrino oscillation sort of thing. But yeah, it would be nice to set some sort of I don't know, bound on the mass of the system in order for us to be able to see these peaks, you know. So I don't know, I guess it's just not 100% clear to me what's the threshold on the mass, or how massive or how light, let's say, yeah, how massive or how little mass.
That's larger than any of the skills in the program.
Yeah, so I think the short answer is that it depends on what you want to check, right? Because for example, part of the reason why I chose this mass and not anything much larger is to retain space-like entanglement harvesting here. Because what happens is that as you increase mass, right, it tends to suppress space-like entanglement harvesting. So you still have this sort of oscillations for higher mass. I actually checked for slightly higher masses, but what I wanted to be a clear indication back then was that I want a parameter space where when the detectors are effectively space-like, they still have entanglement harvesting. That's what I was aiming for. So if your goal is to really study the interior of the light cone, right, then I think it is a separate interesting check that how far this oscillation goes when M goes really big. Yes.
Yeah, it's like assume that I have two detectors and I couple them to the field in regions that are not space-like separated to a massive field. Is it possible to determine whether or not I have harvested entanglement from the field or out of the communication thing, you know?
Yeah.
That's essentially the question. So how light does the field have to be in order for this to be possible?
Yeah.
That is the question, essentially. So it's like, if I start decreasing mass, I'll start seeing like less bounces for these,
yes, in fact,
things, right?
at some point, right, when m is like around 1/100 times, in this case, I use t. You can use omega if you like as a scale.
Yeah.
If you decrease to like around 1/100, right? Essentially, this plot is going to look like the negativity part is going to look very like massless scalar fields.
All right, I guess that this is what I wanted to know. So you're
Yes.
saying that if the mass of the field is like 100th of the detector gap, whatever, then
In fact, 1/10 is more than enough.
okay, then I will be able to distinguish whether the detectors are entangled due to the field or due to themselves. That's the
Yeah,
thing,
I think so. So you will get something very close to this kind.
Yeah, I'd like to see this sort of like comment, like, you know, like, I don't know, in your paper once it's published.
Yeah,
Would be
it's
great.
something that I only managed to get to work only like I only managed to make this work only very recently. So it's it's a great
No,
idea
perfect.
to make this comparison, but it's something that I was also expecting. I didn't expect m to be like, it doesn't have to be really like 10⁻⁻⁶ in order for you to be like a massless scalar field, but it's kind of an interesting comparison. Yes.
No, nice. That's
Anyway,
very cool.
all of these results, you can just add spatial smearing and the answer just trivially got fixed. But I don't want to put smearing because it mixes the causal connection.
Right, any more questions? All right. Well, if there aren't any more questions, let's thank Ericsson again.
So should I stop sharing?
Yeah, I'm going to stop the recording as well. Thank you, Ericsson. Really good talk, very clear.